this administration. And again, if the Palestinian thing hadn't happened, people would have just lined up to vote for her, ignoring the Ukrainian deaths and the Russian deaths. So let's move on, folks. So this is going to be a quick review, and so I'm going to another textbook, and I'm going to this guy here, Mr. Krantz. He was very cranky. Definition, and I think things are working out. Riemann. So our last assignment after the next one is also the proof in this exam 2 assignment. The video is online too, so you can watch that if you want to do that. Our last assignment will be using integration, and there'll be a choice of 2 poems. So this will show up in the last exam. And then as soon as I'm done with that, I'll do random topics that we missed. The last exam, so in the next exam is the same, the one that we talked about. So the last exam, we only have 3 assignments, unless somebody wants 4. There is no hope for that one. Okay, Riemann sum. Okay, so we did this on Wednesday, and this is another definition from another textbook. And the reason why I'm doing that is when you think of the limits of Riemann sums, it makes more sense. So what we're doing is we're looking at the Riemann sums and integrals in a more intuitive but still formal method. So let this closed interval A be, let this thing be an interval, and let f be a function with domain, or you could say on this with domain. This is how the book states it, this thing here. Okay, so how do we represent that? I'm going to draw the line where the inputs come, where the domain is going to be hanging out. So this is our right, this is our x, this is where our interval is sitting. And then it says let f be a function on this domain, as in it is on this domain where f is defined. So let's do this. Here we go. Is that good? So let AB be an interval. So for every point between A and B, if you stick it into the function, you're going to get a value, a function value. You will hit this, right? Every point here is defined. If I choose this point here, let's call it C, I'm going to run into a point here that will be f of C. If there was a hole here, then this is not true anymore. F is then not let f be a function with domain. This means f is defined on this. That the other way to say that is f is defined. Right now, f is not defined because I took a random point C, and the value of the C is not there. All right. Okay. So, and there are other things that we looked at last time. Now let's do this. So this is what we get from this line. The second line of the definition of Riemann sum, according to our textbook written by this guy here, is if we have this situation, and then if P is a set, so we have P as a set which has these elements. And I'm going to do, it's K, but I'm switching to N. So we have a set P, which contains these numbers, these real numbers. And when I have X here, that means they're going to probably go on here. And it's a part. So P is a set. And let's call this set a partition. Is a partition of this thing. So let's try to, let's put this in there. So P is a set containing these numbers. These are finite numbers. They go all the way to n. N could be 10. If n is 10, we've got 10 numbers here. If n is 5, we have 5 numbers here, real numbers. And we take these real numbers and partition this closed interval into subintervals. So, and the way we do it, we looked at it last time, is that A, let's give X naught is going to be this guy here, A. And then B will be our point Xn. And then we're going to throw these guys in the middle anywhere. So I can just randomly go and say, hey, how about X1 is here? X2 is pretty close to X1. What I did is, so these are closer, then the third one is here. And then we're going to have dot, 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 and then Xn minus 1. Xn minus 1 is this number, the number previous to this one. Without any, there is no. So if if n is 5, this would be 4, folks. Let's just do that. So I think I'm going to make n equals, if n is 5, then this is 4, and this is 5. So there are how many subintervals? 1, 2, 3, 4, 5. One less. Okay. All right. So I just did that. So I put this in, and then the squares, the rectangles that we find the areas of go underneath. What's the next thing that the definition says? And if for each j, so j is a number, Sj is an element of Ij. Now, what the hell happened here? Sophia, what's going on with the I? So I is a subinterval, right? So over here we have, this is our first subinterval. How did I represent it last time? Okay, so we have, yeah, like this. This thing here. This is a subinterval. This is not going to, you guys see it in, yes, I have, yep. But I'm worried that is, oh, actually you can kind of see it. So what goes in here? X1 minus X0. What goes in? So these are our subintervals. The maximum of this guy, from here it looks like this is the widest width of the rectangle. So this will be the, so this is X2 minus X1. So here we go. And then this guy here is X3 minus X2, and so on and so forth. So then it says for each j, Sj is an element of Ij. So each of these things are called This is a subinterval. This is subinterval number 2. This guy is subinterval I1. Hmm. Oh, you did shit. They were trying to predict how late you were going to be. Yes. So J is a natural number. And then when you put J here, we're saying that there is not just one subinterval, but many. As in, if J is a natural number, then J goes 1, 2, 3. This is all what we did yesterday, but in a very quick. Yeah, it was an I. Here we go. So J is a set of natural numbers. It's the index. Okay. I is, okay. Let's do it here because, okay, we have this. We have A and B. What is A and B? It's a closed interval that we are displaying, representing on the real number line here. Okay. Can we call it I? We'll name, so this is our name for this interval called AB. Now, what if we did this? Let's say this. So now we take the elements from the partition and sprinkle them on this closed interval, making sure that the endpoint, the left endpoint, gets x naught, and the endpoint here, the right endpoint gets xn. And then we can throw these guys in. So I throw this guy x1, this is x2, this is x3, and let's say this is xn minus 1, the number previous to that. Now what do we have? The situation we have is we created a partition, we took these numbers and threw them into this closed interval. What that does is the partition creates subintervals in I. So our first subinterval that we get is this one here. Let's put them here. So this is now x1, no, sorry, x naught, comma, x1. This is what this should be I1. Right? Then this thing here is going to be I2, which is, this is x2, comma, x1. This is, no, oh, that, and that would be the width. Yeah, so that would be x1 minus x0. This would be the width. Then this thing would be x3, comma, x2. So this is still a subinterval, and we should call it what? xi3. So let's look at this line again. And if for each j, a set of natural numbers 1, 2, 3 to n, Sj is an element of each of these intervals. How many intervals? J intervals. 1, 2, 3, right? So we have another one here. So this is going to be, let's just do this as in x. Why am I messing up here? Yeah, that is shit. I did mess it up. So this should be, sorry, if you were taking notes, please fix your notes. This should be x2 and x3. They only reverse when we do that. x3, comma, xn. It's easy to mess this up. And then the last one here would be x minus 1, comma, xn. So the subintervals are this list here. Yes. Now what do we do? Now it says that choose 1 point, 1 point per subinterval. So which one? I could choose this endpoint or this one, or I could just take this point. And this is our tag. Remember, this is our tag from Wednesday. That's the tag thing. Okay. So if I go back here, and those who have done calculus, if you remember, when you put a rectangle here, you either choose the right endpoints, the height of the length of the rectangle, or the right hand length, or the left hand, or the middle. And what we're doing is we're doing a very generalized version. So we just choose any point randomly. So let's say we pick, this is x1. So let's pick this guy right here. So this will be our S1, and this goes all the way. This will be the height of our rectangle. Okay, which means that our rectangle is going to look like that. So this will be our first rectangle. We calculate the area of this rectangle, which is the width of this thing times the height over here. So this would be F S S1. All right, let's go. Let's do this one here. What if I picked Sj to be the middle randomly? Because it's all up to us. So this is S2 then. And this will be the height that will give us this guy here, S2. And our rectangle is going to be this big here. Randomly, right? I'm going to go ahead and choose this point to the right. This is our S3. So this will be the input that goes into the function. This will give me Fs of 3 here. And here is our rectangle. Thank you. All right. So what's next? So I'm going to delete this one here. So what does the partition get us? The partition gets us, partition allows us to subdivide the closed interval AB into subintervals. Then we get to choose random points on each of these subintervals to be the point from which we measure the height of these rectangles. Areas of all these rectangles, if added up, gives us the Riemann sum. The approximate area, not the exact, of the region of the area of the region below this curve. Because what's the formula for finding out the area of a rectangle? Take one side, multiply it with the other. But so we have three vertical sides. The other one is curved, so we don't know how to do that. So what we do is we know how to measure the area of a rectangle. We don't know how to measure the area of a curvy line, a graph that goes like this. And so what we do is we stick the method of exhaustion, as I talked about on Wednesday. So the next line goes, and if you're confused, I'm going to put up the video I did on Wednesday online. So then this will make a lot of sense. Then if this is the situation right now, what is the situation? We actually do not have any of this stuff. Okay, so this hasn't happened yet. All we have is, let's put S4, Sn minus 1 here, and let's choose this to be our, let's choose this guy to be our Sn. According to this line, for each of the j, each subinterval, choose and put this point there. Once you have this situation, then you can say that given this situation, we can now calculate the area under the curve and approximate area under the curve and that thing is called corresponding Riemann sum. And how do we write what a Riemann sum is? Anybody? R. What's the notation for Riemann sum? There are two things. Do you remember? The function and the partition. Do you remember this from Wednesday? No. We did that. So this is Riemann sum. Okay. And then what I'm going to show next, you remember. And then it says add up, right? Add up. Let's just use, we can use, I'll just use I because that's what we used last time. I goes from 1 to n. So what goes in this one here? This is the height. Should I stick for my first subinterval? Should I stick x naught? Should I stick x1? X1 will take me all the way up here. Or should I use S1? X1 and S1, actually, let's do this. So then it will be a better question. And let me clean this up. Oh, deleted the wrong thing here. Okay. We got X1 here. And I chose my Sj, which will be S1 here. So for what goes here? X1, X0, or this guy? S1. This is the tag. We've tagged it and we've chosen our value here that will give us the best height possible. Okay, just by inspection. And since this is a formula for all we'll just put in Sj here or Si actually. Let's do J. So J here, and then what goes here? This gives us the height, and now we need the width. Width is the right endpoint minus the left endpoint. So this is going to be x, and if I use j again, we would have j here, and sorry, j and then j minus 1. This is the right, and this is the right endpoint and the left endpoint. And this gives us the width of the base. At this point, we can also now do what? We can draw what I had drawn before. So then our first, this is the area that we're going to calculate. So if you expand this, the area here would be f of S1 times x1 minus x0. This gives us the area of this triangle plus, now I just did the 1. Now when j is 2, we're going to get the area of this triangle. And I deleted, let's say we choose the right endpoint to be our Sj. Why not? S2 is Sj, S2. This is our S2. This will be the height. And therefore, our rectangle will be like this. So this is our second one. So this is a plus. S2 x2 minus x1. This gives us the area of this guy. The third S3 is right here. And then our triangle is going to go like that right there. And so on. Okay. All right. So we did this in great detail on Wednesday. This was kind of like a quick review with a definition from another textbook. Now let's do this. All right. Oh yeah. So before we look at the next definition, what happens if I do this, folks? If I take the limit as j goes to infinity, if I apply the limit to a finite sum, all the errors, where's the error here between these two guys? This part of the region under the curve is not getting calculated. But if we make j go to infinity, which means that the number of subintervals are going to go to infinity. You have to take off, right? Yeah. So number of subintervals will go off to infinity, which means all the rectangles will become narrower and narrower and skinnier and skinnier. And so we can then put infinite number of rectangles under the graph. And that will be the exact. So what if we take the limit of the Riemann sum, we get the exact area of the region under the curve of the graph. Bye. All right. So let's do the next definition. Sorry. How lost are you? No, you're good? Okay. All right. Everybody's good. Excellently. Yeah. Actually, so before we do that, I'll do something quickly here. This one's dead. Okay, if I write this, P equals so what's that set? That's the partition containing these guys, right? So this is a set. Set P is a partition containing these real numbers that we will throw in here, right? Okay. So let's throw them in. I'm just doing a quick review. This has to be x0. This is x1, x2, x3, and then this is xn. Let's just make this n minus 1. Now, what if I did this? When we do this, what are we? When we place these points from partition P into this closed interval AB, what we have done is we have subdivided AB into non-overlapping subintervals. In other words, what we have actually done is we have created this guy, x0 and x1, which is this guy right here. Yes? So now what is the partition looking like? Now a partition is a set that contains the subintervals that we created from the x1, x0, x1, x2. So the second way to think of a partition is a set of points Partition is a set of subintervals, set of points in AB. Then partition is a set of subintervals in AB. So what's the second one that we get? X1. See these repeat. X2, which is right here. So this is our second subinterval. And then this is our third. And then this is our fourth. So I'm going to go ahead, write this one here. All right, so now there's another partition that we can think of. This is called the tagged partition. Tagged partition consists of ordered pairs of a subinterval, comma, the tag. So let's go in. Here is, and when, so we're going to have an ordered pair that's going to have, so what should I put first? A subinterval, so the first element. Jake, where did you go to sleep? What are you doing here? He is so committed. Educational moments are coming. And we need to talk about your future again. I say finish your education and then go on that great walk to the Wall of China. Yeah, just wait. Yeah. I want to put a Wall of China in front of Jake. Him and his destiny, Wall of China. Chinese will come and stop you. Okay, now, Miss... I am, yes. Emma, what goes here? A tag partition, and we put a dot here that represents tag. So we're going to go with T. Yeah, so S will become T and J is still I. So first we'll put, so a tag partition consists of ordered pairs of subintervals, comma, tag. So this is our ordered pair. So I'm going to stick this guy in here, right? Comma, the tag. And this will be, in this case, T1. Comma, our second element of this tag partition will be this guy, comma, T2. And then our last ordered pair will be so this is what we did yesterday. So, okay. So a condensed way of writing this would be, let's do that. That's going to be fun. So, oh yeah, we forgot to put the tags. How do we put the tags? We go to our subinterval and go, hey, if I took this to be T1, this will give me the best rectangle that will capture that height under that bit of the graph. So T1 goes there, maybe T2 is here, T3, let's see, this would be Tn minus 1, and then this would be our tag Tn. Okay, and then I was going to do something. All right, we're going to move on to the next definition. Okay, are we good so far? This is the, and then what happens? Where do the Where's the graph, folks? Ashu. There's our graph. And where do the rectangles sit? Right here, right? This is the base. The subintervals become the base for placing the rectangles. All right. Now, this is something we did yesterday. This is a quick review. Oh yeah, I forgot about what we were going to do here. Let's do a generalization of this thing here. So this is our tag partition. X naught, X1, and then the tag is right here, at T1. And so we're doing the opposite. So usually in the book, you get the condensed version. So the condensed version goes, it's going to have how many ordered pairs? Just one. But in fact, you're right, it's going to have 1, 2, 3, 4, 5, all the way to the n. How do we do that? We write n equals 1 here. And I mean, this could go to infinity, right? So we could even stick infinity here. Okay, so I put here what? X. So if I have X1 as my second number, no, Xi as my right, this is actually I, and this can be N, sorry. If my right endpoint is Xi, then my left endpoint, which comes before, would be one previous to that. So this would be, anybody? Excelente. And then the tag would be, so as you go, 1, 2, you create that. Okay, all right. Now let's go do the definition. So this is the idea of the fact that in the limit, the Riemann sum is actually gives you the exact area, is the Riemann integral or integral. How do you say it? Integral. Shit, I can't say these words. Let's do this. So we're looking at definition. And then on Monday, we'll quickly go over the exam again because now it's due on Wednesday. And then there's a theorem that we have to go do involved with all this stuff. So limit, this is a good intuitive but formal way of understanding Riemann sums. So what's a Riemann sum? This thing is a Riemann sum, right? And I'm going to give here space. And I'm going to have, this is a terrible, this is again quick review. So here's our sigma, which is a summation sign. And then I'm going to have Ti here and I from 1 to n, and then x. Yes, is that true? This is called the Riemann sum. And this is what it actually is. So this is the notation. What has happened is Riemann sum had a partition, a tag partition. So there are tags. And the partition created subintervals, which actually, this was wrong, folks. This is the width, right? Created the subintervals whose widths are, width is written here, height is written here. Now, is this the exact? No, for instance, if I just put triangles underneath? Rectangles, sorry. Why do I keep saying triangles? Yeah, thank you for stopping me. Internet, rectangle. Okay, where's the, does the rectangles under the curve, I was going to say triangle. Rectangles under the curve, do they give you an approximate area, right? Because this region is not covered. But what if we made these rectangles skinnier and skinnier so they fit in better and better under the curve? Now, the area that the area that is not getting captured by these rectangles are becoming smaller. So if we send this guy to infinity, rather than having 3 rectangles, and I did all the pictures last time, or that was on Monday, I think. Yeah. So what do I make? How do I take this approximation and make it exact? By what do I do to the Riemann sum, which is what this thing is? This is the notation for Riemann sum. I take the limit on the Riemann sum. In other words, I stick the limit here as I goes to infinity. Then this whole thing can be represented as with this symbol that you guys have seen before. This thing usually in books, it looks like this, right? So delta x sub I becomes d of x, the differential, and then the height stays that. So if you take the limit as I goes to infinity of the Riemann sum, which is an approximation of the area under the region under the curve using the method of exhaustion of fitting in as many rectangles as you can. If you can fit in infinite of them, you will get that. All right. In other words, there is a number that exists in the world that gives us the exact area of the region. And so if that number exists, in other words, if the limit exists, then we have the integral. So that's when we let the, oh yeah, I have to do one more definition. We let, I know I'm super excited, but okay, let's do this. I forgot about this. This is called the mesh of the partition, and we're going to have where is the mesh? We got 3 minutes left. I kill it. Yes, thank God. I told my one section this morning, we're going to have a very short class, and then I went overtime.